It was a cold and dark midterm season. Business wasn't good. The Sicilian found out that I didn't properly test my cartel software. So I was demoted to a courier. I was to bring the Platinum Walkman to someone they referred to only as Monsieur Maison. However, soon I discovered this job wouldn't be so simple. Because Monsieur Maison was not the only one after the Platinum Walkman. And it wasn't long until I allowed it to fall into the wrong hands. This tutorial we are doing stack and queue, we're doing the iterator, and we're doing runtime efficiency. Our stack and queue are not going to be the most optimal, they're going to be the easiest to code. That is the least lines of code written, very easy implementations, and we're going to see later on in this tutorial how that affects the runtime efficiency and where we can do some optimizations later on, perhaps by using a doubly linked list, to make the whole thing work a lot faster. We can see which methods are O of n, which ones are O of 1, which ones should be O of 1 when they're actually O of n, that kind of deal. We're also going over the iterator, which is very useful because it lets us create for loops with our data sets. So when we implement the iterator, we will be able to do a for loop through our stack and through our linked list. And we could do our queue as well if we wanted to, but it didn't touch on it in this tutorial. And we're going over runtime efficiency and comparing the mathematical functions like n squared, n factorial, n log n, O of n, O of 1, to the actual real runtimes of these methods that we just wrote, to see which ones they line up with and how they can work, what they're bounded by, these kind of important details, and we're trying to make that tangible. So enjoy the show. Starting off on that, we'll open our IDE. I've got a link for our code along project today. I'll just send that over to you guys into the chat. It's also on my courses. So once you guys have that cloned, and I'll show you how to clone it from here because I don't have it cloned on this virtual machine yet, I will resume. Today we'll be doing stuff based on our previous tutorial's linked list. So if you remember last time we were debugging this linked list, this time we're going to use that linked list that we just debugged in order to create a stack and a queue and in order to implement iterables. So now I'm just going to say VCS up here at the top. There's a VCS button. That's how you clone a project. You go get from version control. Then you paste the link, the one I sent to the chat. Click clone. It's going to clone the repository. It's going to give us access to the code from what we were working on. Here it's a more consolidated project than last time. We've just got list of links and list of links tester here, and I've got no JDK. I'll just use this one, no problem. All right, so we've got the list of links and the list of links tester. Again, for people who just joined, the link for the GitHub repository this time around is right here in the chat once again. Today we're doing stacks and queues and the iterator. And yeah, we'll be proceeding with that shortly once everybody's got it cloned. I can't launch the polling right now because it's kind of broken, but I'll give you guys a little bit of time. And in the meantime, I'll explain to you the concepts of stack, queue, and iterator. So I'm going to be using the IDE of the gods today, Vim, to be explaining this to you. No, I'm not. I guess my virtual machine has, in fact, died. We will not be using Vim. We will indeed be using something else. No, actually, you know what? I'm not going to give up. Still going to use Vim. All right. So in today's fantastical tutorial, we'll be learning about stacks and queues. So a stack first. Stack is a data structure which is last in, first out. What that means is that when you add something to a stack, it's like, imagine a stack of dishes when you haven't cleaned your house for a while. They're all stacked on top of each other. And you can't just take a dish from the middle or the bottom, it's going to fall over. You can only just take the one from the top or add another one to the top of the stack. If I were to make a stack, for example, let's call this a stack of cell phones, right? I can add more cell phones to the stack, but I can't suddenly query a cell phone from the middle. I'll have to, work my way down the stack for it to work, right? So that's a stack. We stack things on top of each other. Something is added to the stack. We can access it, but we can only access the thing at the top. Hopefully that's clear to everybody. Hopefully you guys don't have too many questions about that. It's a very simple data structure, right? The difference between that and a queue is that a queue is going to be first in, first out. So the one that you put into the stack first, let's call it this little Samsung here, right? This is the first thing we added to our stack. This one will be the first to come out after we add everything. So we add stuff to the top, and then we take stuff out of the bottom. And that is not good. I dropped my BlackBerry. Well, yeah. So we've got this. We can pop things out of the bottom and put things onto the top. That is a queue. You can imagine a queue to be something like, when you're going to the grocery store trying to buy toilet paper and there's a queue of hundreds of people, in the lineup. You've got to get through the first person who got there, the second, the third, all that. So let's add that to our little notes package today. So queue, first in, first out. So implementing a stack is really, really trivial. Stacks are the easiest thing in the universe to program, especially if you have a linked list already. Like, they're basically nothing at all. All you have to do is say there's push, which is add a node to the end of the list. And then there's pop, which is remove and query a node from the end of the list. That means remove and query means you read what is in the node and then you remove it from the top, right? Then also you have peek, which is just look at the top node, and that's it, right? Really, really simple. This is super easy if you have a linked list. Now, queue is not so easy, right? Let's think about it. How do I import GitHub files on Eclipse again? You'll go, I'll show you. I'll finish with this first, and then I'll help you out with that, all right? So here we've got a queue, which is first in, first out. That's not so easy as a stack, because a stack, you just put things on the top. The queue, let's say the head of your list is at the bottom here, right? Well, you have to either swap out, well, yeah, the head of the list is at the top, the head of your list is at the bottom, however you want to imagine it. But regardless of how you implement it, you have to access both the head and the thing that's the farthest away from the head. And that's not very hard because, well, you can always go through the list and get to the end. But the problem about that is runtime efficiency. Like, if I'm doing my queue such that I have to get rid of every single thing on the top before I can access the end, it's going to take me forever to do one of the two basic operations, which is to add things or remove things from the queue. That's not good. So we have to think of a better way to run the queue. And we can't really do it very easily with a singly linked list. But what we can do is we can use two linked lists. So again, I'll just write down the methods here. We have inQueue, which is add something to the list, to the top of the list. We've got dqueue, which is same as pop, but from the bottom. And this one is same as push. Right? And then here we've got, well, peek could still exist, but I'm just going to ignore it for now. But you can also say peek, same as dqueue, but don't remove. And now the way we're going to talk about implementing this is with two linked lists. So rather than having just one linked list, which goes doing all the work, we can have two. But just to note, it's super easy with a doubly linked list, because you can just use the two heads to do everything you need. Or it's kind of easy with a singly linked list. And now for the singly linked list, we have two lists. We have a input and an output. And then what we do is we actually add things to the input list when we add them, and then we can pop them over into the output box, or the output list, and then we can query the output list from the correct order. So a little note, when you pop a stack out onto another stack, it gets into reverse order. It's because when you have two stacks like this, let's say you're maintaining two stacks. When you pop from one into nothing, so let's say I'm creating two stacks, I've got one big stack here. If I start popping over, it's going to be in the reverse order of what it used to be. So when we pop from one stack to another, the order is reversed. And that's useful for making a queue, because if we then pop from one list to the other, and then read from the list that we popped to, that way we can have a reversed one that basically acts like a queue. So two lists, input and output. In queue. Oh, low disk space. Oh no. In queue is it's when you push something to the input. And then dqueue is fill output from the input, and then pop from output. Should be simple enough, hopefully. Any questions from anyone about the concepts of stack and queue? All right, I will take your silence as a no questions, no problem. Again, this is the basic Q stack, last in first out, Q first in first out, Q or stack is super easy, Q is slightly less easy, but still not too bad. To get the project into Eclipse, you will launch Eclipse, let it take its time to open as it really loves to. Oh yeah, what's up? Stack would be considered last in first out, which would mean that the reason it's called last in first out is that you have a stack of things like this, right? The thing you put in last is the first thing to come out. Imagine a stack of dishes when you're washing your dishes. The last dish you add is the first dish you wash because you're not going to go through the bottom of your stack. Yeah, queue is imagine you're lining up at a grocery store and you have to buy some toilet paper and there's a massive lineup. The first person who gets there is going to be the first person who can buy it because they're the first who came. That's like a queue. And then, yeah, a stack is like a stack. All right, I know stack is like a stack is a useless comparison, but still. All right, here in Eclipse, you go File, Import, and then Projects from Git with Smart Import. Then here you type your GitHub URL, which I sent to the chat. I can send it once again. All right, no, not here. You have to click Clone URI first. I always make that mistake. Then it pastes your link, then next, then next, then next, then next a few million more times, and then finish. And then it's cloning, and then here in your project it should come up, and you can open it. And here we've got list of links tester, which is where we're testing, and we've got list of links, which is where we're writing. Hopefully clear for the Eclipse users. Between you and me, switch to IntelliJ, but like while you're using Eclipse, that's how you do it. Okay, over here I can clone the project in IntelliJ as well. Since my virtual machine crashed, can't show it on there. I'll have to do it here. So we'll go VCS, Git, not Git, get from version control, paste the link, clone, give it some time, opening it in a new window. For me, it's a new window. You can use the same window. It doesn't matter. All right, we're going to start going on this. And first things first, let's just get into the stack. Now, the stack should be really, really easy. The stack is, again, just an implementation of a linked list with a special case. And in fact, we're not even going to have to create a new class. I mean, we could. And you know what? We may as well create a new class. But I'm not actually going to write a fully new class. I'm just going to say stack. And then I'm just going to extend linked list. If you remember from the previous episodes, we can extend a class list of links. And it's going to be generic as well. Everything is generic. That's what the E is about. Just going to mute that. So yeah, stack is just going to extend list of links, and stacks have a few methods. Stacks have a public pop, which is going to remove the latest added thing and return it. Returns the latest added thing. Right. Now, I'm just not going to write it yet. I'm going to write all the method definitions first. Then we have a method called peek, which is the same as pop, except it doesn't remove it. So I'm just going to copy paste our description as well. This one will not return anything. I'll just say return the last added thing. Shouldn't have copy pasted that. Last added thing. All right, then we have another one, which will be push, and that's a void method. And this one will add a thing to the queue. All right, so how about we go first with pop? Now remember, pop adds the just the first thing we added. So let's look at our method of list of links, or let's look at our methods in list of links, and let's see what could potentially be a useful method for us to make pop. Well, one thing that we could work with is the method we fixed last time. Remember in last debugging tutorial we fixed remove last? Well, this one is going to be pretty useful, so we'll take note that that exists. And but do we? No, we don't want to use remove last, right? Because pop this is a data structure which is first in, or last in, first out. So we don't actually have to remove the last one, depending on how we run the list. It can get confusing because it depends on how you run your linked list. Do you consider the, how do you consider it? But really it is just as simple as removing the last one. There's a problem that it is not technically as fast as it could be if we use the last node. So what we might want to do is we might still want to do the dual stack implement, or like the a dual implementation, where we are able to do it in O of 1. But let's just call it a get last. So let's just say e last equals get last. And now we can say remove last. And this will, in fact, do a pop. And now we'll return last. And that is literally getting and returning the last thing in our stack. Now peek will just return get last. And push will add e. And I forgot to say e data. Data, push data. All right, seems really simple, right? It's like overly simple how this stack system works. But again, this one is not fast because look, our remove last method is quite slow. If we look at remove last, where is it defined? It goes traverses the list, blah blah blah. It does a traversal to get to the last node. It's not actually that fast. So we could actually implement this a lot faster. Given a slightly different list, and if we use, we could use the same method as with the queue and use dual lists, or we can use a doubly linked list. It's not going to be as fast as is ideal, but that's an implementation of pop. It's gonna pop will just return the last thing you pushed, and then we can write a tester for this afterwards. But also we want to implement a queue. So to implement a queue, we'll just call it queue. And it'll also be generic, but this time we're not going to extend the stack because the queue is not actually a like an extension of stack. It's an implementation of something you do with a stack. So we're going to say private stack e, and we're going to inputs, or not, yeah, private, and then we're going to have a private stack, and there's a few ways to implement this. This is actually a pretty slow and bad way to do it. But it's also the easiest way to explain and kind of the easiest way to do quickly. Well, not even the easiest to explain, it's just the easiest to write without a doubly linked list on hand. And then we'll have a public void enqueue, which will take an e item. And all it'll have to do is it'll have to say inputs dot add item. And then we'll have a public void dequeue e item, which will say if the outputs is empty, which it may be or may not be depending on the situation. We'll say while, and well, this is basically just clearing out the inputs. Input, while inputs are not empty, so while there's stuff in the inputs, outputs.push, inputs.pop. So what this is going to do is it's going to take the output array and it's going to fill it, or not the output array, the output list, and it's going to fill it with stuff from the input list, which is going to reverse the order. So if you've got two stacks, we've got the input and the output. Let's say this is the input, it's completely full, and nothing's in the output. What's going to happen when you hit this method is things are going to be popped off into the output, like so, and it's going to reverse the order. So it's suddenly going to become in the right order. It's going to become, as a queue should be, a first in, first out data structure, because it's going to reverse the order when it does this. And now, after all that is done, we can just say return outputs dot pop. And now this will not always be called. What's wrong with returning outputs dot? Yeah, I forgot to make it return e. All right, and now we need a constructor just to set our lists. So public queue. Did I do it wrong? Oh yeah, no, it's public queue, just without the generic. Public queue, and now we're going to say inputs equals new stack, outputs equals new stack. All right, perfect. And these are all okay. Well, they could be final. I'm not going to make that change right now. But here's an enqueue and a dequeue method. Again, enqueue adds a thing to the queue. The thing we are adding. we're adding. And then dequeuing is getting get and remove the last thing. It doesn't take an item as parameters. What am I doing? Get and remove the last thing, or the first thing. First thing we added. All right. Now return first thing added. All right. So we've got a queue and we've got a stack. Now let's see if we can test whether it's working properly. The code is on GitHub. Yeah, the code is on GitHub. There is the link. The solution code will be posted later. Again, I'll note that this implementation is slow. All right, and I'll also note to you guys that this implementation is slow. They're not the fastest, but let's see if they work in the tester. So now let's test our stack methods in our tester class. You guys are welcome to code along. How do you guys reckon we should test the functionality of the stack and the queue? Anybody got any ideas? All right, well, when we're testing, usually we want to be comparing what our method is doing to like the sort of the pseudocode, what we imagine the method should do. So let's say we have a stack, and they're going to be a stack of, let's say, integers. So we're going to say stack integer nums equals new stack. All right. Now we're going to say, we're going to create a few numbers. We're going to say integer num is equal to, or let's just say 1 is equal to 1, integer 2 is equal to 2. I know this is not exactly the best practice, but it's okay. Integer 3 is equal to 3. And then that's all we really need to test our push and the pop. Now let's just say nums dot push 1 nums dot push 2. Oh, I guess I could have just done that, but whatever. Heh. It's okay, we'll see. 2. Now nums dot push 3. Okay, so now what do we expect to come out when we pop it? Do we expect it to come out with 1, 2, 3 in the order we got them in, or do we expect it to go 3, 2, 1? Could we use the breakpoint debugger to view the state of the stack? We absolutely could use the breakpoint debugger to view the state of the stack. But I also just want to show the behavior of it like this, because looking at the breakpoint debugger will not necessarily show us how, in what order it's going to pop, because the breakpoint debugger doesn't take into account the functionality of methods. Yeah, my camera does that sometimes. It's very, very high tech, I know. Yeah, so we know the functionality of it is not necessarily determined by the breakpoint debugger in this situation, because we want to see the behavior of a method. We don't necessarily want to see the state of the object, because the state of the object just depends on the linked list that it's based on. So we care about what it's coming out in. So I'm just going to say system.out.println nums.pop, and we'll say while nums is empty. Just gonna pop everything out of nums, and let's hopefully, if we did everything right, if I didn't screw it up, we should be in 3, 2, 1. No promises, of course, but should hopefully be the correct implementation. Oh, it's still running a bunch of other tests, and we never even call that method. Amateur hour mistake on my part. No problem. We're just gonna comment out all this, or not even comment out, we're just gonna delete all the nonsense from last tutorial, and I'm just gonna write test stack methods. Run that again. Oh, look, that's crazy. 3, 2, 1. That's because, again, we're doing this as a stack. All right, now let's try the queue version. I know the method is called stack. It's not neat. Actually, that bothers me. So private static void test queue methods. So, okay, guys, how would you expect us to test the queue methods? Do you guys have any idea how we could do a similar test for the queue? If you want to suggest code, yeah, do the same thing. Essentially, yep, we can copy paste all we did. All we have to do here is we're just going to change this to a queue. We're going to say it's a new queue. And then here we're going to say q dot in q. This just goes to show how similar the data structures are. They're all like, oh, very similar. IsEmpty is not a method of q. Oh yeah, because it doesn't extend linked list. So we have to write our own IsEmpty method. And now this is going to be dequeue. Let's just write a quick IsEmpty method in our queue because that's something that's useful. So public boolean is empty. Return this dot inputs is empty, and this dot outputs dot is empty. Okay, so what this is saying is it's saying that it's if the output and the inputs are both empty, it's empty. Otherwise, there's stuff in the queue. That's because the outputs and the inputs they never have duplicates. All the data is in either one of them. There's never overlap in both. So now we can try our test queue methods. So test stack methods. Now we'll do test queue methods. Not with the debugger, but okay. All right, so here we can see that the stack does 1, 2, 3, the queue does 3, 2, 1. Stack and queue are really easy. It took me all of 25 minutes to do like a kind of mediocre implementation of it, and I was explaining it really slow. And like you guys could probably do it in the same amount of time as long as you understand the concept. Stack and queue are really, really easy. They get harder if you want to make them time efficient, but not that much harder. It's a really easy concept. But of course, if you have any questions, ask away. It is crucial you understand the concept of these because it is quite important to things we'll see later on in the course and just in your computer science time. So if you've got questions about them, ask away. But the implementation shouldn't be too bad. If it is, then maybe it wasn't too clear, but hopefully the implementation isn't too bad for you guys. If you have any questions, let me know. Why do you use the Sicilian as the package? Because I didn't bother to change the package from last time. It doesn't matter. Yeah, the Sicilian is just the package I had from before, and I moved the list of links and list of links tester to this, and may as well have that as the package. All right. Does anybody have any wonders about the stack and queue implementation? All right, cool. Just a quick 1 second overview of it once again before we move on. Oh yeah, sure. What's up? Yeah, so the code I just did, I'll explain it through the little notes I did before. So remember, a stack is nothing but a linked list or any data structure. You could actually do a stack from basically any structure, but I like to say it's a linked list because that's kind of what they're sort of based on, maybe. So a stack, you can push to it, which adds a node to the end of the list. You can pop from it, which gets the node you just added and either adds it or removes it. Blah, 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 blah. Seems pretty simple, right? And my implementation of it is, again, quite slow. You can do a faster implementation. It's not very hard to do a faster implementation than what I did. I just did kind of the least lines of code implementation of that. So here we've got stack, which is really easy to implement if you have a linked list. I, in fact, extended list of links because a stack's methods are very similar to the methods of a linked list. They're almost the same. So I just extended list of links. This is the shortest way to do it. It's not necessarily the best way to do it, but it's the shortest way to write it that I know of. In terms of the code, because it's literally just like a one-line kind of deal. And so it's the easiest way if you ever need to implement a stack and you don't care about runtime efficiency that much. That's the way to do it, and you could probably optimize it further. It's not that terrible either, though. It's like the only slow method is this one, which removes last. Anyways, queue. Queue is a little bit more complicated because if you have a doubly linked list, it's just as easy as extending the list. In fact, doubly linked list would make both of these better. But a queue is something that's, in this case, done by having two stacks and using the fact that they reverse to benefit us. So remember, the difference here between a stack and a queue really is the order that things are removed in. You notice how when we printed them out, the stack did it in reverse order, 3, 2, 1, and the queue did it in forwards order, 1, 2, 3. Well, what this means is that all we need to do, essentially, for a stack, or I mean a queue, a bit of a life hack for a queue, would be why not, if the stack reverses it, why not just do the stack twice, right? If the goal of a queue is to remove things in the order that you added them, and a stack does the reverse order. Well, the reverse of the reverse order is the order you added them in. So why not just exploit that little feature of the stack, that it reverses the order of things you add to it, and use two of the stacks to add it to one stack, and then remove it from the other stack such that it reverses twice. Like if we've got the stack, and then we reverse it, like we put it into another stack, whatever, we move from one stack to the other. Now we've got this stack like this. If we remove from it, it's coming back out in the order we added the original stack in, if that makes sense. Or if you imagine like a slinky with like two sides, this is like the slinky going once and then going again, and then ending up on the same side as the original. All right, so that should hopefully be clear on stack and queue. Let me know if you have any more questions. And we can move on to the fun part of today, which is the iterator. Now, you guys might have seen the iterator at some point. I don't know if you've seen it yet in Comp 250. Like, I'm not sure which you've seen, which you haven't. Not quite sure. But we are going to we're going to implement it today. So to implement an iterator, an iterable, is the first thing we need to do is we need to say that our class implements iterable. All right, should be relatively simple that we're doing that, right? We're saying that this class can be iterated on. Now, what does iterable actually do? Well, iterable is an interface, and what this interface allows us to do is the for loop. Anything that you can do with a for loop is actually calling the iterator of a class. So yeah, when you iterate through a data structure, when you use like a for each loop, you call iterable, or you call the iterator. So now if in our list of links tester, we want to say, for example, or why not here, we can say for integer I in nums, right? If we want to do this, if we want to iterate through this with this for loop, we have to implement the iterable interface. So that's what that means. When we click implement methods on iterable, it's going to say that we need to implement a certain method. In this case, it's iterator, which just returns an iterator. Now, it might seem like a strange method because it's returning an iterator of type E, and where do you get this iterator of type E? Like, how does this work? What does this mean? Well, the trick of the iterator is you actually have to make an inner class. You have to make an inner class, which is the iterator, which goes through your list. The reason for that is you can have like a bunch of iterators going, and they're all in their own little classes, and they're all working on it. So before we can make iterator, we actually have to make an iterator. So we can say, we can say class list of links iterator implements iterator. Right, and now this one also is red because we didn't implement all the methods. Let's implement them. Next and has next. All right. So has next, next. How do we do these? Well, let's just say first let's think about how an iterator could work. Right. So what is the purpose of an iterator, and how does it function? Well, an iterator is a class that gets created when you instantiate a certain object. So if I put list of links tester over on this tab, when we instantiate the for loop over here, which it doesn't let me do because the class is still broken, but once we implement it, it'll work. And that's a queue. I meant to do it with a stack. Oopsies. There. So once we instantiate this for loop, what it does is it creates an iterator object, because the for loop calls it. Like inside of the code for the enhanced for loop, the iterator object is called, and the constructor is created. And then for every item in this data set, it's going to call next until has next returns false. So while has next is true, it's going to call next repeatedly. That's what the for loop does. The for loop calls next until has next returns false. Right now, has next just returns false right away, and so it'll never actually do anything. If we make has next return true, and we actually make our iterator return new list of links iterator, and we don't want to throw this exception. I don't care about it. All right, now it's just going to null pointer exception the hell out of us because, well, it's not going to null pointer exception us. It's just going to null us over and over again because every time it calls next until this one is false, right? So if we wanted to really make a broken thing, we could say return I broke this, right? And then here, well, that's not a E. All right, so I guess return I broke this, but cast to an E. That's going to be really bad. That's actually pretty terrible. I don't want to do that. I'm just going to say return null still, sorry. That would have been fun, but I don't want to make everything based on strings. So if we make this, say let's say we have a counter. Let's say I want to break this. I want it to print null 10 times. So I want the enhanced for loop to loop 10 times. I can say int I is equal to, or int counter, I'd say, is equal to 0. And now we can say counter, or we can say if counter is less than 10, counter plus plus, return true, else return false. All right, now it's going to print null 10 times because, well, we told it to write null 10 times. So that's a little function of the way that the for each loop works. Why do you use the @override keyword? The @override keyword is generated by IntelliJ, and it's just there to let you know that this method is overriding a method in the superclass. It doesn't actually do anything, it's just an annotation. But it does help you when you're writing to remember which ones are overridden from a superclass and which ones are your own methods. So here, again, we're using the counter in order to tell it how many times to print null. But what if we actually wanted the iterator to do its job? Well, then the change we make is not too hard. All we have to say then is instead of, let's say, return null when the counter is 10, why not say if counter is less than this dot size? Does this have a size parameter? No, it's just size. It's less than size. Now it's going to print null for every single element in the linked list. It should print it 3 times. So can you guys see how we're getting closer to our solution, how we're getting closer to writing the iterable, or the iterator? We've now gone from printing null once to printing null 3 times. Well, 3 is the same as the number of our data set, so maybe instead of returning null, we could actually return something from our data set. And remember, the counter is keeping track of the index, essentially. So we could just say get counter. And now, oh, index out of bounds exception error. We've got to keep track of that. Our counter plus plus is in the wrong place, and we're iterating it in has next. That's not good, because remember, we're iterating the counter every time we're checking if it's empty or not. Don't like that. So instead, we should be iterating that here. Or we can say eData is equal to get counter. Then we can say counter plus plus, and then return data. And now what we're doing is we're counting up the counter after we query the data, so we won't miss index 0. And now if we run it, well, it doesn't look like that impressive of an output, but if you notice that, we just used a for loop on our stack. Now that might be useful, because see, the for loop is a really simple and intuitive way to write your code. Imagine having to actually write the while loop every time you're using your linked list, like a while, whatever next is not null. That's a lot of work. So why not just do this? It's a much easier implementation for when you're writing your code later. This one is quite slow because it's got to traverse the list each time. So this is slow and bad, but it's all right. It works. And remember, the iterator it's really simple when it comes down to it. Like, this is all the iterator really needs to do. You can do faster versions of the iterator. For example, you could actually, if you wanted to, let's say this wouldn't be faster, but this would be an interesting thought experiment. You could create a data structure inside of the iterator and then use that data structure to do has next and next, which sometimes it's a good solution, sometimes it's not. But here, let's say you can make an array of from your data in your iterator and then traverse through it. Again, it's probably not the best solution, but and there's got problems with it, because if you create another data structure, you better have immutable things and keep track of your items, because if you do any changes to them in the for loop, well, they might not apply if you just do it with a deep copy. But anyways, we've got this iterator now, and hopefully that's clear to everybody. Does anybody have any questions regarding the iterator? Okay, I'll go over it one more time slowly, just for anybody who might still not get it. The iterator is a interface, and so is iterable. Iterable is an interface which applies to a data structure. What it means to be iterable is that it can create a for loop. So our list of links is capable of creating a for loop, because it implements iterable. Now, in order to implement iterable, you have to be able to return an object of type iterator. Now, the object of type iterator is something that you have to define yourself, and you usually define it as an inner class of your data structure. So here, my iterator method gets the iterator, and it just returns a new version of the list of links iterator, which is an inner class that I have defined. The inner class list of links iterator implements the iterator interface. This iterator interface is what tells it, well, basically to have a has next and have a next method. It's what the for loop calls when in the actual code of the for loop. And I demonstrated kind of how that works by making it return null forever, and then return null a certain number of times, and then return stuff from our data structure. So here, we've got our hasNext method, which just determines whether or not there's another item in our data set, and our next method, which gets the next item in our data set based on this counter. And that's what the for loop calls. Hopefully, should be a relatively trivial thing for you guys to implement. Now, just to demonstrate that we can use not just this kind of for loop, but, well, this other kind of for loop doesn't actually use iterators. So if we want to say for int I equals 0, I is less than nums dot size, I plus plus, system dot print line, or what's it called, nums dot get I. This kind of for loop works too, but this kind of for loop does not call the iterator. So if we say put a print line in the constructor of our iterator, I'm just going to say, for instance, public list of links iterator. This constructor is blank, it does nothing, but it will it'll just demonstrate to us when the iterator is called. So this is about print line, hello from iterator. We could also use breakpoints for this, but I just like to have a clean printout for today. Very simple. So yeah, the iterator is called for the first for loop. It's not called for the second for loop because this one uses iterator, this one does not. That's not an iterators. If you have any questions, floor is yours. Otherwise, we can move on to showing off the runtime efficiency of these various things. All right, so let's, to test the runtime efficiency, first I'm gonna put these solutions up on GitHub. We're going to call it solutions. Put that branch up there. I'll put that on GitHub. All right. So now you guys should be able to see the solution branch on GitHub. In IntelliJ, to change your branch, just click at the bottom here. We can go to master, which has, well, nothing at all. It's just the blank one we started with. And we have solution, which has the solution code. Now we're going to show off the runtime efficiency of all these different methods and show you exactly why certain methods I said were slow, certain methods I said were fast. Don't take my word for it. We're going to peep that out using a magical tool, the holy runtime efficiency tester. All right, so if we just take these files, I'm going to drag them on over there. I'm just going to put them into this package. I didn't want to move them. I wanted to copy them. Whatever. I'll quickly get them back on this project as well. Ignore that blunder on my part. And now we're going to write a runtime efficiency tester for our list of links. So we're going to see how fast these things run. This is a tool I'm using. Well, we'll see if... Yeah. Oh, it's because I was already using a queue. Test qualifier. What's going on here? Concurrent link to queue. It looks like my my queue method is interfering with my it's interfering with my existing use of queues in this program. So let me just fix that first, and we'll get into debugging this. All right. So now we're going to go into our benchmark definitions, and I'm going to write some speed testers for our queue. So I'm going to call it. This is just my benchmarking tools code. So name is equal to, let's say, our queues in queue. Our expected runtime efficiency we don't care about, and our category will be tutorial 7. And now public long test in queue long size. All right, let's write this out. So to test runtime efficiency, remember we take the start time and end time between things. First, we're going to create a data set. We're going to use the same data set creation system as I did for a previous method. Is annotation a context manager like in Python? The annotation is not something that's within the scope of Comp 250, way out of the scope of the class. It's an annotation. It's used for reflection, which is a program reading its own code. the reason I have this here is that I have this tester generate code based on the code that's written in it. It's some meta stuff. It's complicated and it's not part of the course. It's just something for my own use. Nothing to do with what we're doing here. So here I've got a data set, which is in a concurrent linked DQ. We just want it to be in our queue. Queue runtime tester, and then we're going to say is new queue. And now queue dot, we want to test in queue, right? So we'll do in queue size -1, and we're just going to fill it up right to the brim of where we need it to be at, and then we're just going to say date d equals rand dot next date. I'll generate a random date, and then I'll say long start time equals system dot nano time. We'll say dataset dot enqueue d, and we'll say long end time is equal to system dot nano time, and we will return end time minus start time. All right, now let's see how our enqueue method runs. If we run this, fingers crossed everything works properly. Takes its time to start up. All right, and we've got our method here. Let's compare it to some common runtime notations. You guys should all see the graph coming up. In green is our enqueue method, and here are the Java built-in methods. No, we want to see the mathematical ones. So we've got O of 1, O of n, O of n squared, and O of log n. Our method, keeping track of it, is yellow. And which one do you guys think it lines up with best of all these big O notations? So here we've got in orange, we've got n squared. Here in green, we've got n log n. In blue, we've got O of n. And in purple, we've got O of 1. Which one do you guys think? Yeah, it lines up with O of 1. And that's a lot better than, well, different methods that we could have done. Like if we did a list traversal, it'll be a lot slower. So if we compare this to O of 1, we can see that, yeah, it's basically just lining up with O of 1. The definition of O of 1 is it doesn't change over the size of the data set. So let's make our data set really, 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 really big. Oh, that was a big spike in our Q's and Q. I guess, remember, big O notation is not a hard and fast rule. Chances are what happened there was my computer was doing something in the background, like processing the video I'm recording or something else, and it made that spike. I would ignore it. Let's just make the data set massive. Making the data set massive did actually kind of slow down our method here, which is unexpected for O of 1. So what I did was I turned up the size of our data set to really massive. And it's actually looking like over a really long time span, it ain't looking so hot, Chief. But let's compare it to the DQ method of the built-in Java one. Yeah, it's still pretty bad. It's going up and down, right? But to strictly say it's O of 1, it should be kind of close to O of 1, but I'm not too sure. It's actually not behaving super well. And that's probably a result of the inefficiencies of the way we coded the system. So if we look at in our queue, well, it's literally just adding it to the inputs. Well, what is adding it? It's, oh, it's not pushing it. That's another item. But if we look at our push method here, add, okay, now if we look at our add method in our list of links, yeah, well, no, it's keeping track of it, and then it's also traversing through our linked list. So in reality, we thought it was O of 1 because it was really close at the start, but when we do big data sets, we see that this actually causes it to be O of n. And it's just because each step takes a very short time, because it's a very simple step every time. It actually works in O of 1, but I would expect it to be somewhere around O of n in reality. So if we look, and we compare it to O of n, with the really, really, really big data set, we're just going to make it massive. O of n and R in Q actually line up pretty well when we're working on a really, really, really large data set, or they should. See, they both spike up. Now, our Q doesn't spike up as fast. We can adjust our time per step to be very small. Not light theme. No, nobody likes that. Now, we can see that they kind of line up reasonably well, like O of n. And how do we find, where can we find it? This tool is not released yet for the class. We're going to try to release it for you guys later. This is just a tool I've been using for my own demonstrations. So yeah, we can see that it kind of lines up with O of n. Like the slope of it lines up with O of n. So that method is actually working in O of n. Don't get tricked because it was fast right away. And that's just something you kind of have to feel out and you have to realize. Like when you're working with huge data sets, things do change. And the efficiency of our methods does matter, and this one was not too efficient. So let's try benchmarking a few different ones as well. We'll go into our benchmark definitions. I'll just copy paste this template and I will add a couple more. So I'll say our queues DQ. And then we'll say test DQ. And now I'm going to say our data set's full size. And in here we're going to say dataset.dq. All right, that one's going to be pretty simple to write. Now we're going to do our stack, not that. We're going to do our stack as well. We're going to say our stacks push. And we're going to call it push. And now here we can say our stack date is equal to new stack. And now here we're going to push. And now we're going to push again, and we're going to do a -1 on the size over here. And now, you see, it's really easy to say, do these testers once you've written one. You can just copy paste them for most of your methods, especially with data structures. So you can see here, I'm just living the lavish life, doing very little effort, and getting these testers built. So test pop, dot pop, and that takes no inputs. All right, so now we've got all the methods we wrote today, and we're going to graph them all, and we're going to watch how they run. And some of them are going to be real bad, and hopefully at least a couple of them are going to be decent, but I'm not too sure. Oh, and I forgot to change the notation. Our stacks pop. All right. We got them. We don't want to see all these. We just want to see our stuff we made. So here we've got our stacks push, our stacks pop, our queues DQ, and I forgot to say our queues NQ as a different one as well. Silly me. Test NQ. NQ? No, that's there. Why is it not showing all of them? Test DQ, test push, test pop, long size, all these seem the same. Pop, push, DQ, NQ. Weird why not all four of them are showing up. I did write this morning, so it might just be bugged right now. But we'll just try that one more time. Queues DQ, our queues NQ, our stacks push, our stacks pop. Okay, well we're just going to forget that our queue is able to enqueue. That method never existed as far as stalling is concerned. So here we can see our different methods. We can see our queues DQ is a lot slower than our stacks pop. Oh, our stacks push is in the graph. I guess it's just the button didn't show up properly. Oh, it's over here. That's why. Okay, so it looks like the buttons overflowed over to there. Oopsies. I have to fix my GUI later. Anyways, our DQ is the slowest right now. Our stacks pop is also in the running for being slow, and our DQ is just slowing down like hi hell. It's a really bad runtime efficiency. If we turn up our steps per iteration, oh damn, that's bad. All right, our queues DQ is starting off real bad, and it's just skyrocketing. I'm gonna guess O of n squared. No, O of n squared is a lot worse. So it's probably more like O of n. Let's see. This is just me comparing it to these different. It's worse than O of n, but it looks like it's changing at a similar rate. No, it is not. Oh my god, our queues DQ is bad. It's like O of n squared probably. It's one of the. It's really, really slow, but it's okay. We did write the least lines of code, not the most optimal one. We can see compared to O of n squared, it's better, but it's like I would still say it's on the order of probably like something like really bad O of n or like a decent O of n squared, because it's no bueno. But our other methods, if we ignore our atrocity of a DQ method and we ignore O of n squared, our other ones are all like pretty solid. Our pop is going up and down depending on whatever is happening to my computer at the moment, but they're all not terrible. Right now we're working with a data set of like 13,000 and it's still working like reasonably okay. So they're not good, they're not the best, but they're not terrible. But keep in mind a queue and a stack are something that should be O of 1. They should be doing everything in O of 1. There's no reason why push and pop and NQ and DQ are not O of 1 methods. So my implementation was particularly slow. I did not write a good queue, nor did I write a good stack. I wrote the least lines of code I could think of given a singly linked list. I did not write the best implementation. And you can see that with the runtime efficiency. If we compare that to the queue built into Java, and I'll compare that to our DQ here, well, we're going to lose terribly. Like the Java one is this flat line at the bottom. That's how much more efficient these things can get. Ours is And later on in the course, probably in upcoming tutorials, I'll show you guys the optimal implementations of these things. But today is just the concept of it. The easy mode, the simple, the quick to write, the thing that's going to get your code working, but not working quickly, so that you can work on improving it afterwards, you know? All right. It's been great, guys. Hope you enjoyed the things. If you have any questions, now's the time.